Hello, I'm from the Colorado Center for Astrodynamics Research at CU Boulder. I work for Professor Dennis Akos doing GPS research. Next slide, please. So I'll be talking about a RFI localization hybrid algorithm that combines time difference arrival and power difference arrival. I'm currently a senior at CU Boulder. Next slide, please. So an overview, I'll be talking about background and motivation, concept, including the overview of localization. Then I'll talk about time difference arrival, power difference arrival, and then the hybrid combination. I'll then go over some experimental results and summarize and conclude. Next slide, please. So going on to background and motivation. Obviously, everyone's talked about satellite navigation being almost everywhere. Military and civilian applications depend on the accurate position, navigation, and timing. U.S. spends about $1.5 billion on GPS, and it has a direct economic benefit of $75 billion, or 0.4% of our GDP. However, jamming and spoofing are on the rise, whether it be from these $15 or less personal privacy devices that trucks can buy off like eBay, or targeted electronic warfare. But in order to keep the user confident in their GPS, the jammer spoofer has to be detected, localized, and mitigated. And it's important to localize in order to remove the source of noise or spoofing whenever possible. So our solution is to have a unique interference localization method that includes hardware and software. Our hardware is a Lego setup that includes an FPGA, FX3 board, and our NT board. And basically, we can use GPS, GLONASS, Galileo, and Beidou all to for our centimeter level accuracy for our receiver. And then our software is where the hybrid localization happens. So we're in between the identifying, using in between detecting and mitigating, where we localize. And basically, we just hybridize the time difference arrival and power difference arrival. So looking at localization as an overview, many methods exist now that can localize an emitter. TDOA is by far the most used and has been around since the days of Lauren and Omega and probably before. Power difference arrival, frequency difference arrival, and angle of arrival are also other methods. And TDOA and FDOA has been combined effectively to locate moving emitters. But today we'll be talking about TDOA and PDOA. So why TDOA and PDOA? On its own, TDOA is very accurate, provided that it is able to obtain its precise GPS solution for time synchronization, or as long as you have some time synchronization, then TDOA works great. But without synchronized time, it can only be propagated a limited distance without large errors. And then PDOA, on the other hand, requires no GPS solution. Only the automatic gain control voltage data is required to gauge the incoming power of the receiver. However, PDOA by itself is very inaccurate due to the errors in the path loss coefficient and multipath. So by itself, it's really not that effective of a technique. So together, they provide the best of both worlds. TDOA can calibrate the PDOA's inaccuracies, and then once calibrated, PDOA can provide a better estimate when the GPS solution is no longer available. And specifically for CW jammers, PDOA can also discern between several of the TDOA correlation peaks that happen specifically for the CW jammers. So going on to time difference arrival. So TDOA uses the difference in time it takes to get to one receiver versus another to then create a hyperbola of possible points. And then with several pairs of receivers, those hyperbolas can intersect at a the jammer's location. And then to find this time difference, the raw IIF data from each receiver is mixed to baseband and cross-correlated. This is just an example cross-correlation peak I see usually. The delay in samples is multiplied by the speed of light and then corrected for synchronization errors to get you that difference in distance. So results for TDOA alone are very good. It's often correct within 10 meters in nice situations, but it does depend heavily on sampling frequency with option of interpolating samples, but obviously the higher the sampling frequency, the longer the computation time. And now PDOA. To characterize the power received by each receiver, the automatic gain control is used. So this is like nominal AGC data, and then when you see these jammers, the AGC is lowered, so like it adapts to the power that it receives. And then the change in voltage from its nominal value is then converted to a dB equivalent using calibration curve for a specific type of jammer. And it's pretty linear in the regime that we have the AGC power in, like 0.8, 0.7. So it's a nice relationship to convert from AGC to power. And then just with an example path loss coefficient of 2, the following results were found where we see that the red X is very far from the truth location. And you can change the path loss coefficient to match it up, but in real situations, you really can't do that because you don't know where the truth location is. And so that's why it's the limiting factor. Next slide. And then combining the two. So we assume a valid GPS solution to begin with, which gives us a correct TDOA estimate. And then this TDOA solution calibrates the PDOA's path loss coefficient, and then each different combination of two receivers using PDOA is examined and then weighted to the correctness of the TDOA. And then the calibrated PDOA is combined with the TDOA just by summing up their contributions in a nonlinear least squares algorithm. And then PDOA starts with a low normalized weight since it's inherently uncertain. And then if the GPS solution is lost, then the PDOA is given more weight and carries the TDOA through that jamming or spoofing. Next slide. Experimental results. It shows a nice animation of these lines following this road. Basically, the car is driving from this point to this point, and the TDOA hyperbolas follow that point. It's just showing how accurate TDOA is, basically. And it does show Doppler shift causing most of the errors. We can go to the next slide. This would be another animation of a stationary situation where it accurately stays around the truth location of the green X. You can go to the next slide. And this is the stationary example where most of the points are within 10-meter radius. This just shows how accurate the TDOA is by itself. And then when we look at PDOA on the next slide, this is the dynamic case where it actually does follow the road pretty well, which was surprising to me when I first saw it, but makes sense because the difference in power is the main driver. And if it's changing compared to each receiver, then it'll actually do pretty well. But in the next slide, where the stationary receiver, this is stationary and yet they're all over the place. So that's why we really can't trust the PDOA by itself. Some are hundreds of meters away. Next slide. And then when we combine the TDOA and PDOA estimates for the black X, which is the hybrid algorithm, you can see a balance between the two, which is a good scenario for the hybrid algorithm. And then next slide will show the stationary, where we can't trust the PDO estimates, so the hybrid algorithm stays with the TDO estimates, or the TDOA estimates. So not a huge advantage with the stag emitter. It doesn't get any better or worse, but at least it doesn't get worse. It really has its use cases for the dynamic and the jamming when you're completely jammed cases. Next slide. And then we'll finally go on to summary and conclusions. So TDOA is fine until the time solution is lost. PDOA is not accurate, but only requires the power from AGC voltage, and it's more accurate in dynamic emitter situations. And together, they can leverage each other's advantages. Since it does not degrade the stag estimate when the GPS solution is still valid, that's very good. And then in dynamic cases, it leverages both estimates to provide a better location estimate. And then future work is obviously more tests, statistical analysis, and incorporating FDOA and AOA to enhance solution, as well as different frequencies that can provide the timing information when needed. Questions? Yes?
I appreciate all the work you guys are doing on this one. My question is pretty simple. Again, I'm a simple person, having, much like our other guy here, kind of spent some time in the middle of nowhere. So how long does it take to get to the 1 centimeter and the 10 meter resolution? So if we use the hybrid technology, if I'm standing there, how long until I have a 100 meter or a 10 meter or 1 meter resolution?
So the resolution wouldn't really, basically you have a bunch of receivers that just get sent to a server, and then you would get the resolution the max resolution that you can get from those receivers within like 15 seconds. Like you would get probably a 5-meter estimate at least. I'm not sure about the time it would take to improve that estimate. More work has to be done. Yep.
Did you guys consider directional antennas?
Yeah, we'll be doing angle of arrival stuff.
I
Oh,
guess
sorry.
what I mean is, if your jammer is using a directional antenna, then your PUA is going to be biased by that.
Yeah, the PDOA wouldn't be effective for that. But TDOA would still be, so that's why the hybrid really works.
I guess I'm considering this hybrid solution. At least from what I understand, your hybrid solution is utilizing measurements from the PDOA and TDOA. But if you have a directional antenna, now you have a bias in your PDOA measurements.
Mhm.
And I was just wondering if you consider the effect of that bias that it might actually pull up in TDOA solutions.
Haven't directly considered that.
There are commercial systems that do something similar to this. Have you compared your results to theirs?
No.
So, I mean, if you want to look at the delta between your power difference of arrival, there is probably some threshold in terms of where that delta is and what your main power levels are to be able to come to a solution.
Yeah, I wouldn't be able to tell you a threshold, but it does depend on the receiver itself, like the resolution of the AGC. Some receivers like give big steps, some give very small. The ones I use are very like almost analog, so it's very. You can still make the PDOA solution, but obviously the better, the bigger. So, thank you very much.